So, therefore, in the last class we saw that how qualitatively simple shear flow uniaxial extension or biaxial extension can be described and visualized qualitatively. Now, we will try to describe it quantitatively, and the description is based on the flow that velocity is basically given as only in x direction, and both v y and v z are 0, and of course, the velocity gradient exists, and that is nothing but gamma dot y x, and we can define a deformation measure which is can be indicated using a symbol E y x or gamma y x. Now, again in our course we will use E as a symbol for talking about strain, and also the strain which is infinitesimal strain tensor. So, E is infinitesimal strain tensor. So, as the name suggests, this is valid for small deformations. In solid mechanics, generally this is indicated as epsilon when it is tension or compression. It is indicated as gamma when it is shear. Okay. Again, these epsilon and gamma and all are commonly used terms, but when you want to describe the complete details you must use a tensor. So, which is the strain tensor. So, that is why we will go back and forth between these symbols which are commonly used symbols, but the correct and complete term which is the strain tensor itself. So, that is why given that a material is deforming at this gamma dot y x, you could define deformation which is gamma y x or E y x, which is basically the amount of deformation which is taken from present to any time tau. Whenever it is time in the future, we will have strain being positive because the basis is present time. When it is in the past, then the strain will be different sign. Okay. So, since the basis is present time, we can define it like this. So, now let us just look at how do we describe the position of each and every material particle. So, this is the overall flow, and we saw that the velocity is gamma dot y x times y. So, now let us try to describe the position of a material particle as a function of tau, because tau is equal to t means present, right, but we would like to find and the position of a given material particle at any tau. So, we will indicate x tau, y tau and z tau as position of a material particle at time tau. And of course, we would like to express it, given that we are tracking a material particle, that x, y and z is position of the same material particle at what time? At tau is equal to t, which is the present time. So, how do we relate this? So, if you take a material particle which is here arbitrarily, right, any material particle which is there, how do we now describe its position as a function of tau? So, again conceptually it should be easy for us to say that at present time if the particle is here, then somewhere in the future when tau is greater than time, the particle would have moved, right. And similarly, if I take some time where tau is less than time, then the particle would have been to the left. So, now the other thing which I have drawn automatically is the y position of the particle has not changed at all, right, because the particle is moving only in x direction. And similarly, the z motion is not at all described because z nothing changes, it is an infinite plate in the z direction. So, therefore, now can we summarize this? So, clearly we can first write down y tau will remain y and z tau will remain z. Now, how is x tau related to x? What is the velocity of the particle at this point, given that it is y from the bottom plate, right. So, its velocity is given by this. So, what will be the position of red particle with respect to position of black particle, given that this is at tau and this is at t. So, we can write gamma dot yx into y into tau minus t, right. Will it be tau minus t, because that is the amount of time for which particle has moved at a velocity, and this will be x tau plus, does that make sense? So, if tau is equal to present time, then what happens is this term goes to 0 and therefore, x tau is equal to x. And so, of course, clearly at tau is equal to t, x tau is equal to x, y tau is equal to y and z tau is equal to z, and any time in the past tau minus t will be negative and therefore, the x tau will be x minus something. And so, this way this is a complete description of the flow actually. So, now using this we can actually calculate the strain, and to calculate strain we usually use a variable which is called displacement. Okay, so, and it is again a vector because displacement can happen in 3 different directions. So, in this case u x x tau minus x, u y y tau minus y and u z which is z tau minus z, and this is a displacement vector which we will denote using u. So, clearly of course, u y and u z are 0, and this is not a surprise that material is in fact not getting displaced in y and z direction, it is only getting displaced in x direction. Now, the deformation exists if there is relative displacement. Two material particles which are next to each other. So, the one which we have drawn as this black and the other particle which is grey, right, are they getting relatively displaced with respect to each other? Yes, right, because in some time in future this particle would have gone little bit further down and the other particle would have in fact be further to the left, right, because the top particle is moving faster while the bottom particle is moving slower. So, therefore, there is clearly relative displacement, and relative displacement can be used to measure the and therefore, strain tensor, and this is what we had qualitatively discussed also, that strain measure is related to displacement gradient. And what is displacement a function of? U x is a function of x y z, which one? U x, right, displacement is in x direction, but is it a function of x or is it a function of y or is it a function of z? It is a function of y, right, displacement, see displacement is function of y because x tau itself is a function of y, right, x tau is a function of, as we saw, it is a function of y. So, therefore, u x is a function of y. So, again when we do displacement gradient we will again see that diagonal terms will be 0 and off diagonal term, and only in fact x y terms will be non-zero. So, this is very similar to the velocity gradient terms, only thing is velocity gradient is strain rate while displacement gradient will give us strain. So, right now we have not defined these formally, so that we need not do right now. We will do this measurement of definition of strain later on, because for most rheological purposes strain is useful for only solid like materials. So, if we have rubbers, if we have materials which are more solid like, then we use strain. Otherwise, many other materials we will use strain rate and the differential form. Quite often we will see that we will have an integral form of a constitutive relation. So, there we may need to use the deformation or strain. So, since we have not defined it, we can again try to see the relationship between the strain and strain rate by just intuitively looking at what is happening in this flow. So, we have the top plate and the bottom plate, and if we take a look at any 2 points which are let us say delta y apart, and we would like to know what is the shear strain, right, using our older knowledge of basically the amount change in length divided by original length. So, in this case the original length will be in y direction and the displacement is in x direction. That is how the angle comes in, right. The shear is measured using this angle, because this displacement is there and this is the original. So, this is the displacement and this is the original length, measure of original. So, since we know that this particle is moving at some velocity and this other particle is moving at some other velocity, we could write this as velocity at y plus delta y and velocity at this point. So, it will be let us say V x plus del V y by del x into del V x by del y into delta y. So, this is the velocity, and let us say some motion has happened for some amount of time. This minus V x into del t and divided by del y, right. This is the measure of shear strain, and if we take delta t out and take delta t tend to 0, then that will be rate of shear strain or strain rate. So, that will be velocity gradient, because V x delta t and V x delta t will cancel out. So, we will have basically V x and V x delta t cancel out, and then we can say that del shear strain by del t is nothing but del V x by del y. So, for our present purposes we will do this, okay, where partial derivative of time itself is actually giving us velocity gradient. So, the strain rate and strain are related to each other through a simple, but all this is possible when delta t is very small. All, in other words, this is all small deformation. For an arbitrary amount of deformation, what we will need to do is we will need to define rate quantities with respect to tau. So, that is something we will do in future. Right now we do not need to worry about it, but del by del tau of a given quantity of interest, this at tau is equal to t will be the rate of change of quantity. So, remember I had said earlier that strain at present time is always 0, right, because we are using the current state as the basis, but this quantity will not be 0, because we are calculating the quantity in this running time, and this is called a convected rate. We are moving along with the material and evaluating the derivative in the continuing time, and if you are interested in the rate of deformation at present time, then we just substitute tau is equal to t, we will get the present time. And so, what we will see in fact is, let us say del strain measure del tau at tau is equal to t will be the strain rate tensor. However, for small deformations is d, okay, its partial derivative itself is fine. Just the way, in fact, that is what we showed here. This that we showed is partial derivative of shear strain is just equal to the velocity gradient. That is in general not true. Okay. We have not discussed this, but in one of the future classes we will derive. First of all, we have to define strain, right, and since we need it only for more solid like materials, we can postpone. So, lot of discussion in next set of lectures. We will only worry about small deformations. We will only look at material deformation which are small. So, in those cases we can use this relationship, where strain and strain rate are in fact derivatives of each other and simple derivatives. But in general, for a complete description we must take the convected rate of strain to get the strain rate. As a measure of deformation also we should use a strain measure which is not small e, but it is. So, there are several names like finger strain tensor, green strain tensor. So, some of these we will define. Again, there are multiple options, unfortunately or fortunately there are multiple options in which way we can define strain, but all of these strains will reduce to E as for small deformations. So, this is again a point which we can emphasize for small deformations. I think we have said this before, but we will just remind ourselves that all strain measures will reduce to E. And so, in the beginning of the course we will continue to use E. So, this is what is summarized here, that you can write this tau minus t as a gamma yx, another variable which is indicative of the strain, and therefore, this is what we derive, that x tau is x plus y gamma yx. For any time in the future gamma yx is positive, any time in the future tau minus t is positive, therefore, gamma yx is positive, and therefore, x tau is more than x, which means the fluid particle has moved to, material particle has moved to the right or in the positive y direction. We also did this, that we defined the shear strain as a small incremental amount of time, and this is only valid for small deformation. And of course, we will be using Eyx or gamma yx interchangeably, but all of these are for small deformations, and of course, it can be written in terms of the strain rate tensor also, because these are derivatives with respect to time. So, the same thing can be done for uniaxial extensional flow also, where we can define again the position at any time with respect to the present time. So, x tau, y tau and z tau, and how are they described as a function of x, y and z. But before we do that, first let us try to describe what is the flow. So, how do we what is the velocity field? Just to remind ourselves again, this is the flow, right. So, it is getting extended in z direction and getting contracted in x and y direction. What components of velocity are non-zero? All three, right, and what are they functions of? So, you can see that the shape completely remains the same, which means there is Vz, but it is not a function of x and y. Similarly, Vx is not a function of y and z, and so on. So, in general what we can write is Vx is a function of x, Vy is a function of y, and Vz is a function of z. And what we also said is we can have this pulled at a constant rate. So, this rate is constant, the rate of pulling in x z direction. So, therefore, we can say del Vz by del z is constant. We will denote that using epsilon dot. So, velocity Vz is epsilon dot times z. What about Vx and Vy? They will be negative, and Vx will be minus half epsilon dot x and Vy will be minus half epsilon dot y. So, which implies that at the center of the cuboid velocities are all 0, x equal to 0, Vx is not there, y is equal to 0, velocity is not there, and z also velocity is not 0. Now, can you look back and try to justify what I had said earlier, that position will be changing exponentially in extensional flow. The stretch ratio we will define, which is with respect to position, right. Epsilon dot is the velocity gradient and strain rate term. The stretch ratio is defined in terms of relative displacement or in terms of strain. So, in fact, that we will do, but that will be exponential, because Vz can be written as del z by del t epsilon dot z. So, how does z change as a function of time? Log of z will be epsilon dot times time. So, therefore, this, and so that is what is described here, where lambda x, lambda y and lambda z are the stretch ratios, which are relating to relative position. If lambda x, lambda y, lambda z are 1, that implies that there is no deformation. This is the stretch ratios. We have multiple symbols being used. We will have a set of problems which you can work with, so that you can become familiar with some of this notation, because here onwards when we start discussing rheological properties, we will start specifying epsilon dot is constant, epsilon dot is varying as a function of sine time and so on, or gamma yx is constant or gamma dot yx is constant, because our interest will be in studying the material behavior under those conditions. So, we have to remember in the back of our minds that how these quantities are related to each other, and conceptually when we say simple shear, what is happening to the material, so that we should be able to understand the material behavior. Just as a last thing, we can stop by looking at this. We looked at lubricated squeeze flow. What if now again the same rotational rheometer we use, and I take the fluid between the two platons like earlier, and again like earlier I squeeze it, but now this is not lubricated squeeze flow. So, which means there will be no slip at the top and bottom plate, and top plate is only moving in z direction, bottom plate is completely stationary. So, now what will be the velocity profile in this case? One thing is clear, is fluid will moved out in the r direction, it is getting squeezed out, but what is being forced is the r velocity on the top and bottom plate has to be 0, and therefore, you would expect that the velocities to be possibly something like this, right. Well, this is r direction and this is z direction, okay, because you are squeezing fluid, and now this is an example of a shear flow. See, so that is why based on the rheometric experiment that we are doing, we first will always need to identify whether this is a shear flow or shear free flow or a combination, and more importantly we will at times have to understand the fluid mechanics of the flow. Under what condition does it make sense for me to write a velocity profile like this? Right now we have not worried about fluid mechanics at all. So, at least for the first month of the course we will not, we will somehow say that somebody else has done the analysis and made sure that the flow profile is like this, but there will always be some squeeze rate, some conditions, some separation, which will ensure that fluid mechanically the assumptions are correct. For our first section of the course, we will assume that somehow fluid mechanics information is managed in such a way that we achieve a flow which is well described. As a practitioner of rheology, we will have to worry about, when I am doing rheology, are these conditions being met or not. Okay. So, therefore, understanding of fluid mechanics of rheometry is also important, but that we will look at sometime later.
So, as we have emphasized that fluid mechanics of rheometry is very important, and assumptions related to the rheometry will have to be satisfied for us to get good rheological data, which in the next few sets of lectures we will assume that such conditions are met. In general, looking at the slide here, we will define what are called material functions, and these material functions enable quantitative measurement of material response, because we are doing analysis of rheometric flow correctly, because we have assumed the type of flow, because the geometry of flow has been designed appropriately, and the variables which have to be controlled are being controlled perfectly. So based on all these assumptions and achievement of rheometric flows, we define and characterize the material function. So in general, to do this, the instrument will have to be basically manipulated in terms of controlling some variables and measuring some variables. And of course, these variables could be torque, force, position, or rate of movement. So for example, keeping position fixed would imply that we will impose a constant strain. If rate of movement is constant, then we may have a constant strain rate. And so these are all the variables which we could measure or control depending on which type of flow. And therefore, this combination of analysis of rheometric flow and measurement and control allows us for estimating and quantifying the material functions. We will see that each of these material functions are called so because unlike material constants, so basically in case of Newtonian fluid, viscosity is the material constant. In case of conducting solid, the conductivity is a property of the material, and therefore it's a material constant. But we will see in the case of course on rheology that the material behavior cannot be described simply based on a constant but a material function. So we will see that, for example, viscosity is a function of strain rate itself. So therefore, we choose to call all these characterization in terms of material function as opposed to material constants. And so in the next slide, we have summarized again that in rheometric flows, our objective will be to achieve a certain controlled flow, which could be shear flow or which could be a shear-free flow. Of course, all the assumptions regarding fluid mechanics in terms of one-dimensional flow, narrow gap to ensure that Reynolds numbers are low or the flow is in a particular manner, basically will ensure that we are able to do the quantification of material functions. And in general, when we do the rheological analysis, we will see that there are 4 or 5 very common ways of looking at and measuring material functions. For example, if we keep constant strain rate, then it's called steady shear. And in that case, we define something called a steady viscosity. But we could also keep constant strain rate, but look at how the stress changes as a function of time. And so in this case, this is not a steady state measurement. We look at stress growth. Eventually, of course, the stress will become a constant. It may, in certain cases, not become a constant, but generally we will expect it to become a constant. And so therefore, stress growth is another type of measurement. We can keep stress to be constant, which is called a creep measurement. We can keep strain constant, which is called stress relaxation. And of course, we will also see that a very important part of rheometric analysis is to do oscillatory measurements, in which case either strain or stress or even strain rate are varied in a sinusoidal manner. So there is an increase, decrease based on sine theta, cos theta, or other sets of sinusoidal functions that we are familiar with. In addition to these, of course, there are more complicated deformations such as double step strain or superimposed oscillation. However, in this course, we will not really look at these, but learn all the basics with the very standard set of rheometric flows which are achieved to define the material functions. So in each case, for example, with constant strain rate and constant stress, we will define steady viscosity as material function. With constant strain rate and growing stress or changing value of stress, we will define a stress growth viscosity. In case of constant stress, creep, we will define a creep compliance. In case of constant strain, we will define a stress relaxation modulus. In case of oscillatory strain or stress, we will define a complex modulus or a complex viscosity, which implies that we will have an in-phase, out-of-phase components of these moduli and viscosities, and we therefore choose to call this a dynamic modulus or dynamic viscosity, and we will have the real and imaginary or storage and dissipative parts of these material functions. So these are several ways of doing rheology and several material functions that could be defined based on these. In the next set of lectures, we will examine each of them carefully. Alongside, we will also look at some important models or some very simple models which can be used to understand the overall response quite easily. So with that, we have reviewed the basics of material deformation and fluid flow which is required for us to look at rheometry of material systems.